Alright, now we talk about section 3.2. And here we'll be talking about the domain and range of functions. So let's recall, I want to point out some notation for you. Okay. We're going to be writing things in 3 different ways. We'll be able to write, so that this notation is on page 258. Okay. If you have say for example, an inequality like x is greater than a, the interval notation of that would be a to infinity. A would not be included, so this is where I use an open circle to be a little more clear. And if we wanted to write a description of that, we would say x is greater than a. Okay. So there's an entire list on page 258 for you to refer back to. So in domain, let's recall from last time, okay, we had a relation, and that relation, a relation was a set of ordered pairs, so 2, 10, 3, 10, 4, 20, let's say 5, 30, and 6, 40. Okay. So here's a relation. It is a set of ordered pairs. Okay. And in this one, it actually turns out it is a function. Okay. So now we ask ourselves, well, what is the domain of this function? Okay. So remember, domain, we said was the set, it was the inputs. We also called those the independent, so inputs, usually denoted by x. We also said this is the independent variable. So from a set, here, we could say our domain for this problem is, our domain is equal to the set of 2, 3, 4, 5, and 6. Where the range was the outputs, usually denoted by y, and that's also called the dependent variable. So in this set, our range, it is a set, that's why I'm opening the braces. 10 is in there. We don't have to list 10 twice. Okay? We could, but we don't have to. And then 20, 30, and 40. Okay? That's how we can do that. And so it's very easy when we're dealing with a set of ordered pairs. However, once we start working with functions explicitly, it gets a little more confusing. So, for example, like if we had to determine domain from equations, we need to expand our definition then of what domain is. The domain is really the set of all allowable, okay, so this is the keywords, allowable x values, okay, also the independent variable, okay, so the set of all allowable x values. Well, what does that mean? So, for example, if our function, remember this is our function notation, f of x is equal to x squared minus 1, this is a polynomial. Our basic function here is x squared, so this is a parabola. Okay. And anytime we have a polynomial, there is no violations about what values of x we can put in. We can put in any value for x, and so our domain is going to be equal to all real numbers, okay, which in interval notation we write as negative infinity to infinity. Okay. And that's one of the reasons why we like polynomials. We have no domain violations there. Another example, f of x is equal to 5 minus x plus x cubed. Again, this is a polynomial. All values of the exponents are positive and they are integers. So here's positive and integers. So this is also a polynomial, and our domain is all real numbers as well. Now things get different when we have the rational function. Okay. Now remember, a rational function is some polynomial, we'll call it p of x over q of x. Okay? So it's some polynomial over a polynomial. So we'd like to say that since it's just a polynomial over a polynomial, it could be all real numbers. The problem is, remember, with a rational function, we can't have a division by 0, so whatever that denominator polynomial is, it cannot equal 0. And this is where we're going to find out values that we need to exclude from the domain, okay? Because they will not be allowed in the domain. So, for example, let's say our rational function is x plus 1 over 2 minus x. This is a rational function. It's a polynomial over a polynomial. So we will be fine using all real numbers except the ones that make the denominator equal to 0. So in order to find out what values those are, you take the denominator. Our denominator is 2 minus x, and we want to find out when that equals 0. And now this is a simple linear equation. We can solve this. We find that the denominator will go to 0 if x equals 2. Okay? So this is the problem. We don't want the denominator equal 0, so we can't let x equal 0. So this we exclude from domain. That is, on the number line, we can have every number except x equals to 2. Everything else is fine. So this gives us two intervals. Remember, this goes from negative infinity. This is positive infinity. So this first interval here, the way we represent that is it starts at negative infinity and it goes all the way up to 2, but it can't include 2. Then this interval here starts at 2, but it cannot include 2, and goes all the way up to infinity. And remember, when using interval notation, to say and, we put a U. It stands for the union. So this is the domain in interval notation. This is the domain on a number line. And if we had to do it in set builder notation, remember, we'd open up with a set. We'd put in our generic item, we'll call it x. Then put the bar for such that. And then we'd put the characteristics in here. And so the characteristics is that x cannot equal 2. So that's where the graph that I showed you, or the table I showed you in the beginning, is going to be helpful. Okay. Let's try another one. Okay. If we have f of x is equal to 1 plus 4x over 2x minus 1, okay. Again, this is a rational function. We have a polynomial over a polynomial. We cannot let the denominator equal 0, So simply pull that out. Remember, it cannot equal 0. And then solve this. So we have that 2x's cannot equal 1, so x cannot equal 1/2. On the number line then, the only number we exclude is 1/2, but everything else is okay. This goes from negative infinity to positive infinity. So if we had to list the domain, this area here starts at negative infinity and goes all the way up to 1/2, but it can't include 1/2. Okay, so that's this area. Now this area starts at 1/2, but can't include 1/2, and goes all the way to infinity. And remember, in interval notation, we'll put in the u. Another way to write the range, then, or the domain, then, is the set of all x such that x cannot equal 1/2. And there could be lots of values that we'd have to exclude. It just depends on what values of x will make the denominator go to 0. Radicals will also give us some radicals will also give us a problem. Okay, so for example, if we have even radicals, let's think for example about our basic parent function, y is equal to the square root of x. Okay. Its graph looks like this. This is the point 0, 0. And graphically we know that the domain of this starts at 0, okay, and it can include 0 because we can take the square root of 0, that's 0, and we'll go all the way to infinity. Okay. Another way to say that is the set of all x such that x can be greater than or equal to 0. And why is that? Well, it's specifically because if you let x equal -1, then we have y is equal to the square root of -1, and this is not a real number. So it's not a real number. We only graph in the reals, and so our domain stays greater than or equal to 0. So how, for example, does that affect a function like this? Say f of x is equal to the square root of 7 minus x. Now here we knew that whatever value of x had to stay greater than or equal to 0. But now it's not just the square root of x. We have this entire value under the square root. So it's that entire value must stay greater than or equal to 0. And now if we solve this, we have 7 must be greater than or equal to x. And remember, if we rewrite this, I like to have the variable first. The arrow is pointing towards the x. That's the same thing as saying x must be less than or equal to 7. If we were to put that on the number line, then here's 7. 7 can be included, but I need to be less than 7. So in interval notation, I only have one interval. The lowest value it can take on is negative infinity, and the highest is 7, and it can include 7. So these are all 3 ways to do it. Let's try another. Let's say f of x is equal to the square root of 5 plus 2x. again, the same problem occurs. Whatever is underneath this radical, and let's even make this a fourth root, just for fun. Okay. This is an even root. Okay, we'll have the same problems about multiplications adding up that we had with the square root. So it is that 5 plus 2x has to stay greater than or equal to 0. And now I could solve this. 2x's have to stay greater than negative 5. And dividing by 2, 2x has to stay greater than or equal to negative 5 halves. On a number line, we could graph that. Here's negative 5 halves. That's our important value. It can include that number, but now x has to stay greater than that. So we look there. So in interval notation, the lowest value it can take on is negative 5 halves. It can include, okay, and the largest number will go to infinity. So that's the problem with even radicals. So we have problems with rationals, and we have problems with even radicals. What about odd radicals, though? So, for example, could we find the cube root of negative 1? Okay. Finding the square root was imaginary, but what about the cube root? Well, I could rewrite negative 1 as negative 1 times negative 1 times negative 1. Okay. And in the cube root, I'm looking for a group of 3. Okay. And here is the group of 3. Okay. So negative 1 times itself 3 times would equal negative 1. So there's not a problem there. What about the cube root of negative 8? Can we find that? Well, we can, because we could rewrite negative 8 as the cube root of negative 2 times negative 2 times negative 2. And now there's a group of 3 negative 2's, so this is okay. So as a consequence, what happens when we look at our basic parent function, it looks like this. Y is equal to the cube root of x. And we see that the domain is not only positive or 0, but it includes all real numbers. So then, for example, if we're asked about the cube root of 7 minus 3x, we can look at the index on the radical, find out that it's odd, and we can immediately from there say, well, then the domain must be all real numbers. We could also look at the fifth root of x minus 2. We look at the index here. It is an odd number, and therefore the domain is all real numbers. Okay. Now let's mix some of them together. What if we had an odd radical in a denominator? Okay. So something like this. What if we had f of x is equal to x plus 5 over the cube root of 2x plus 7? Okay. Now we have two things to worry about. Okay. First of all, there's a radical. Okay. Will the radical affect the domain? And the answer is no, because it's odd. Okay. But we still have this denominator problem. Okay. And the denominator cannot equal 0. That's fine. So we'll pull out the denominator, that is the cube root of 2x plus 7. put that equal to 0, because that will be the values that x cannot equal. Now if we solve this, I could cube both sides. Cubing a cube root will undo it. So we'll just be left with the 2x plus 7. And 0 cubed is just 0. And now it's nice and linear. So this is 2x minus 7, or that x cannot equal negative 7 halves. If we look at that on the number line, then here's negative 7 halves. Everything but negative 7 halves is allowable. So this goes to negative infinity, this goes to positive infinity. Our first interval here starts at negative infinity, goes all the way up to, but can't include negative 7 halves, so we put a parentheses. The second interval starts at negative 7 halves, doesn't include it, so it'll get the parentheses, and goes to infinity. Now there's a union in between there. And that's how you'd write it on the number line. Now if we have an even radical in a denominator, we have even more things to worry about. So what am I talking about? Like here's an example. If f of x is equal to negative 4 over the square root of x plus 2. Now we have an even radical. Okay? And once we have an even radical, we have to worry about things staying greater than or equal to 0. And with the denominator, we have to worry about not equaling 0. So what is what? Okay, well with the radical, I have to worry that what's underneath the radical, that x plus 2, that has to stay greater than or equal to 0. So we know that x has to stay greater than or equal to negative 2. That's just for the domain of this radical. Now we have a denominator, and I have to worry about that. That is, the square root of x plus 2 cannot equal 0, or the function will go undefined. So if I solve this, I square both sides, and we'll get x plus 2 then cannot equal 0. So x cannot equal negative 2. Okay. If x equals negative 2, this function goes to 0. The denominator goes to 0, and the function becomes undefined. Well, now, how do we incorporate this? I've got two different sets. Both have a key value of negative 2. The green says I can equal negative 2 and go beyond. From the blue, we have everything but negative 2. So what's the answer for our function? Okay. Well, the function, for its domain to work, everything must work, the even radical and the denominator. So we want to take the union of those two. And where it's true for both values, here it's only true for blue, not true for green, so we'll exclude that. Beyond here, it is true for both the blue and the green. So our answer will be true on those values. The question was what happens at negative 2. And at negative 2, the green has a value, but not the blue. So our answer has to be where they both agree, and they do not both agree at negative 2. So our answer can only go from negative 2, not including, up to infinity. Okay, so that's how you find domain and range of graphs of functions given their equation. Now let's say, for example, you're just given a graph. Okay? To do that and answer the question of domain and range graphically, notice there's a closed circle here, not an arrow. So what that's telling us is that our domain starts at -5, and there is an arrow here indicating it'll go on for forever. So our domain goes from -5 to infinity. It includes -5 because of the closed circle. Now the range, on the other hand, is the set of all allowable y values, or of the dependent variable, or of f of x. Okay? So the lowest value that the range takes on is -infinity from the arrows, and it goes all the way up to, but has to stop at 5, okay, because the closed circle. It does include 5. Now here's a graph that you might see in the newspaper. And we can ask ourselves, well, if we're estimating, what's a reasonable value for the domain? Okay. Now here, notice the increments are in 5. So this is no longer 0. So I would say a reasonable value for the domain, okay, your time will always be the independent variable, starts at 1970 and goes to a little bit more, so I would say till 2010. So domain here, 1970 inclusive to 2010 inclusive. Now for the range, we could start at 0, but it's just a little bit below 200, so we might estimate that a reasonable range here is like 190 up until, now the highest value here is just above 2,000, so we might say 2100 would be reasonable for that, just shy of that. Okay, so these are not exact values, but these are estimates of it. Okay. If we were estimating with this one for domain, it looks like a good estimate is 1950 up until 2000 is a reasonable domain. Okay. Now for a range, the lowest value somewhere in here, say 45. Okay. And the highest value comes up here at 90. So a reasonable range goes from 45 to 90. Okay, so there is another worksheet for this section as well. I'm going to ask you to tell me about the domain and range of some of our basic toolkit functions. Okay, now let's look at the absolute value of x. So if our function is equal to the absolute value of x, if we had to build a table of values from this, we can start with the positive values. The absolute value of 3 is 3, 2, 2, 1. The absolute value of 0 is 0. Okay. Then here the absolute value of -1 is +1. The absolute value of -2 is +2. Absolute value of -3 is +3. So if we were to graph this, here we have the point 0, 0, Then we'd have the point 1, 1, the point 2, 2, the point 3, 3. So this is a 45-degree line. 1, 1, 2, 2, 3, 3. Okay. Now over here, we'll get negative 1, 1, negative 2, 2, negative 3, 3. So it's going to be the mirror image of this. Okay. This is negative 1, 1. This is negative 2, 2. This is negative 3, 3. Now the domain for this function is going to be all real numbers. Okay? There is no value of x that we have to exclude. Now the range, on the other hand, this is the point 0, 0. Okay? Now the range, on the other hand, if I start looking down here, there are no negative values for the function. Okay? The very first value that the function picks up is 0, and then continues to infinity. Okay? So the range starts at 0, it does include 0, and it goes to infinity. So I'll be asking you to do things like this on that worksheet, so you'll be getting these parent functions in your head very clearly. But notice if I look at it this way, on this side of the graph, if I just restrict this domain, really I could think about this as the line y is equal to x. Now, it's not true for values less than 0, but true for values that are greater than 0. We could think about this as the line x, y is equal to x, okay, y is equal to x, where x will be greater than or equal to 0. Okay, that's one graph. Okay. Now, if I restrict it on this side, I could think about this as the opposite graph. I can think about this as y is equal to negative x, okay? The 45-degree line with a negative slope. Okay? Now, if it was to carry on, it would actually come down here. So it's really only behaving like the line y is equal to negative x for values of x that are less than 0. I hope this makes sense. Okay, that is this portion of the graph. Okay. And so in this way, we can either write the absolute function like this, absolute value function as this, or we can write it in two parts and write it this way. And this is known as a piecewise function. That is, I can think about a function in terms of its pieces on given domains. Well, when might that happen? Okay, so let's think about this equation. Okay. Let's say you're at a museum, and the museum is going to charge you $5 a person for a guided tour for groups of 1 to 9. Okay? But once you get a larger than that, like say when you have 10 people, they're just going to charge you a $50 flat fee. Okay? So let's write the function. It's really two different pieces. That is, I'm going to pay $5 per person as long as I have greater than 0 people and less than 10. Okay? So that's just the line, we can think about it as 5x, okay, with a slope of 5, all the way up until 10. And then after 10, I'm just paying the constant function of 50. Okay? In this case, they're just saying it's cost of the number of people, where n is the number of people. So that's another example of the piecewise function. Now, they can come in multiple parts. So let's do another one. Let's say I'm given a piecewise function such that f of x is equal to x squared if x is less than or equal to 1. So that'll be part 1. It's going to act like the constant function 3 if x is greater than 1 or less than or equal to 2. And our basic function y equals x if x is greater than 2. Okay, so this is this is our function, okay, and this is our domain. Now let's start trying to put all this together. Okay? I'm going to do it in 3 parts so we can see how this works. Okay. So we really do have 3 parts. We have the part of y is equal to x squared. Okay. So y is equal to x squared is our parabola. It looks like so. This is the point 0, 0. At 1 you get 1. At 2 you get 4, etc., etc. So this is y is equal to x squared. On its entire domain. Okay? But we're not asked about its entire domain. We just want where x is less than or equal to 1. Okay? So that means we want this part filled in. We want this portion of the graph. Now over here I'm going to draw what the resulting graph looks like. So our first part is x squared for x less than or equal to 1, so I just need the blue part. So it will look like so. And we should label these points. This is the point 1, 1, and this is the point 0, 0. Okay. Now let's move on to part 3. Okay. Now part 3 is the constant function 3. So if we were to graph that, that's just this line, this line, where y is equal to 3. Okay. So that is, so this is the point 1, 3, this is the point 2, 3, down here we have the point -5, 3, it's the constant function. Okay? And it's the constant function on its entire domain. But what we are looking for is the restricted domain. Okay? It's where x will start at 1, not included, so I'll put the open circle, and will go all the way up until 2, and will include it. So this green part is what I need to put on here. When x is 1, okay, I have the open circle all the way up to 2. And this is the point 2, 3, and this, if it existed, would be the point 1, 3. Notice this is passing the vertical line test. Okay, if I fill this in, I'm going to have a value here and here, so I can't have that and still have it be a function. Now, thirdly, we have to look at this function, our 45-degree function, okay? Also known as the identity function. Okay? It looks like a 45-degree line. Okay? And I want the portion of its domain. Okay, so what do we have here? This is the point 1, 1. This is the point 2, 2. We have the point 3, 3, etc. This is the line y is equal to x. Okay, so now I only want this function for x greater than 2, not including it. So I only want where I don't include 2 and go forward. Okay. So this portion of the graph, now if this is 2, 3, I need 2, 2 is down here. And then it will continue on. Here would be a point 3, 3. And so this result is this graph. It is a piecewise function. I'm also going to be posting a worksheet for you. It is examples of types of equations that you could expect on your exam and to get more practice with how this needs to be graphed. Okay, so I think that'll get you through your homework. We're worried about domains, ranges, how to find those algebraically and how graphically, how to write those in interval notation, set builder notation on the number line, and then understanding how restricted domains can lead to piecewise functions. I'm here if you need me. Send me an email.